In this video, we're going to discuss advanced MetPy calculations, how we can add those calculations to a dataset, and then plot them up. To begin, we're going to use the model underscore calculations underscore advection and vorticity notebook. Now, I've already saved this to duplicate it and put it in my notebooks. And so we're going to go ahead and use that one. I renamed it advection and vorticity calculation. Either way, you can go back and duplicate it and get it and rename it if you want, or you can just watch this video. This content is not going to be required for any of the coursework in the remainder of the semester. So the reason this is a separate notebook is because to do these advanced calculations is a bit more involved. And so one of the things we want to do is talk about how can we actually do this. And for those adventurous enough, you can seek to do it on your own. Now, to begin, this is going to be very similar to all the other notebooks we've used this semester. And so we're going to go ahead and import the necessary modules to use, and then gain access to our data to be able to plot up these calculations. Now, if you want more information about some of these calculations, the handout does contain a part 3 called Harder MetPy Calculations on page 6 of the handout. I encourage you to go and find that to then work through this notebook with that. These more complex calculations aren't necessarily complex in and of themselves, but that there are a few more steps to be able to get them into our data sets to then be able to plot. And so there's kind of a 4-step process that's going to go on. First, we need to pull out all of our necessary variables from the data set. Then we need to calculate some intermediate parameters to use in our final calculations. Then we need to actually do the MetPy calculation and then add it to the data array or the data set. And so it's this last piece that's just a bit more complicated. Now we can go ahead and find, since we want to do advection as one of our calculations, a little bit more about how we calculate advection using MetPy. And so we're going to do that, and here we've got to the help pages for advection, and we see that there are 3 pieces that we're going to need. We're going to need some sort of scalar that we're going to advect. We're going to advect that scalar around using the wind, and then in order to do this calculation, because we're going to need gradients of things, is that we need to know what is the grid spacing between all of our data points, for example, from GFS output, and that's what we're going to need for our deltas. And so one of the most common advections that we use in meteorology is temperature advection. And so temperature is going to be our scalar variable. So let's make our way back to the notebook now and walk through this advection calculation. And so the first thing we need to do is specify the level. A very common level for us to do a temperature advection calculation from is 850 millibars. Additionally, we're going to subset by time here to make us work on as small of a bit of data as possible. In order to facilitate our ability to do our calculation, to get our advection, which is essentially our wind vector times our temperature gradient, we're going to first pull off our temperatures at our isobaric levels, then our U component to the wind, and then our V component to the wind. And we are going to subset through the select method by both the vertical level and the time, and so we need to use this MetPy select method to do so. This is going to get each one of these variables down to a 2D array and make them more easy to use in our calculation. In addition to these 3 variables, we need to also pull off our lat lon values for where all of our grid points are within this dataset. Using these lat lon values, we're going to be able to compute the grid deltas, or those dx and dy values, the change in x and the change in y values. And so we can do that and unpack what comes out of our MetPy calculation for that into 2 variable names, dx and dy. Once we've finished all this pre-work, we can now put all of this data into our advection calculation from MetPy. First, we're going to feed in our temperature values and attach our units in K, since we know that that's the units of our temperature. Then we are going to feed it a list of our wind components with units, and then finally our dx and dy grid deltas, which already have units attached to them since it came out of a MetPy calculation. This is where our actual calculation is taking place, but then we need to go through the process of adding it into our data set. And so what we need to do is create this variable into essentially a data array, an X-array data array. In order to facilitate this, we're going to use a couple of variables. And so we're going to set a new variable called dim names, which are the names of our dimensions, because we need named dimensions to be able to plot this data. And so since our scalar that we're vectoring around is temperature, we're going to use the dimension names from our temperature variable to populate this variable. Our variable values are just simply going to be, in this case, our advection values, which we're going to take just the magnitudes, so strip off those units, and then multiply by 3600. The 3600 is going to take our data from being in K per second to K per hour. We could have also used a unit conversion here, but this just makes sense. Finally, we're going to add our attribute dictionary so that we can get our grid mapping features and our unit features associated with it. And then ultimately, we're going to add it to our data set with this ds.assign. Actually, let's go ahead and actually remove this times 3600 and see what we can do there. So let's run it. And it ran successfully. It's added it to our data set. And now we've got a variable that we can plot. And so we're going to plot our temperature advection, which was the name of the variable we gave it up here in our assign. And noting that it was just 2D data, we have to set our level to none and our time to none. And now we're going to plot from -10 to 11 using the cool warm color map with a horizontal color bar. We are then going to add some other common variables such as our temperature contours and our geopotential height contours, noting here that we need to keep our level and plot time in because these are coming from the original data set that we did not subset. Additionally, we're going to add some wind barbs so we know what our vector is, and add all of this, all four of these things, to our plot. So let's go ahead and run it and see what we get. This will take just a couple of seconds to run, and you can see that essentially we have stuff that is just above or below zero. Now, we know that there's actually a bit more temperature advection going on here, but remember our units are in K per second, and so our temperature probably isn't changing all that much. So let's go ahead and try and use our plot underscore units to change our parameter. So we're going to add plot underscore units here, and we're going to do deg C per hour. And let's see if this works. I don't know if this is going to work. And it turns out that it doesn't seem to like. It has no attribute to evaluate. Interesting. Let's try one more time. K per hour. And let's go ahead and make sure here, ds.temperature advection, to make sure we got the units array. We did, and we do see that it is in fact Kelvin per second. So we'll try one more time. And it doesn't appear to have worked. That's interesting. It should have worked, but that's okay. We know we can overcome this issue by going back up here and modifying times 3600. And we can go ahead and rerun this cell. I'm going to go ahead and nix this cell, and now rerun this cell. Again, taking just a few seconds, we now get some better temperature advections going on here that are a little bit above and below zero. We can also change where our contour values. And so now we're going to go from -5 to 5. Notice we went from -5 to 6 there. And here we see now a better range in our temperature values. If we wanted a bit more gradation, we could actually change how we're doing this contouring to get a finer look at it. But that's okay for now. It just shows us how we can actually process and see temperature advection by doing a more complex calculation. We could do a similar thing for vorticity, which is the change in the v component of the wind divided by the change in the x distance minus our change in the u component of the wind divided by the change in the y distance. Here is all the calculation pieces that are needed, and you can visit this website to find out more about how vorticity is calculated in MetPy. But if we go ahead and run that, it runs successfully. Here we've scaled our vorticity value by 1 e to the 5th to get it into whole numbers so that when we go to plot our variable, relative underscore vorticity, which is what we added here in our data set, we get a nice plot showing a large amount of relative vorticity in the base of our trough and anticyclonic vorticity in our ridge. Notice we saw our inability to save there because of these output values. And so we can go ahead and edit, clear our outputs to save, and we're just going to go ahead and rerun this cell at the end to get our image here. So we have our nice image. Again, relative positive vorticity values in troughs and negative vorticity values in ridges. I hope that this has been a useful video to explain how we can do more complex variables even though you won't need it for this semester. The hope is that this will be easier in the near future in MetPy, not to require so many steps. But until then, this is what we've got. Thanks for watching.